and welcome to part 2 of our videos on getting started with KiCad PCB design. So at the end of the last video we finished off our schematic, zoomed in right here, and then we moved over to putting it onto our PCB canvas. So all of the components have just been dropped in a little bit of a mess and they're ready for us to go through and lay them out. So we'll start off. Well, I'm going to go through a few things. I'll walk you through a little bit of what tools are available on this canvas as well as within PCB Designer, and then we'll go through sort of laying this all out. So again, on the left hand side we have a few things that control things like the units that we're working in and the grid that we're looking at, as well as some different things we can do to constrain the lines, which all of these things can make it a little bit easier to lay stuff out, but have a look through, play around with it. I'm just going to leave it with its defaults for now. Then across the top, we've got a couple of tools again, similar to what we had before. We've got footprint editors that allow us to change the footprints of our components. We can view the board in 3D. So at the moment, it'll just be that kind of mess of components with no connections at all. And then we can also do a design rules checker. So this is sort of similar to the electrical rules checker from the schematic tool, where it allows us to just check that everything is actually connected and meeting any design rules that we manually set. And yeah, that's pretty much the main stuff there. Then along the right hand side, we've got a couple things going on. One is that we've got the different tools for actually putting stuff onto our board. So we can place footprints by choosing particular ones. Don't need to do that though because we've generated everything from a schematic. We can wire stuff together using the route track button. We can also change the length of tracks, and there's also a few other things around drawing filled zones which we'll use to create a ground plane later on, and some different shapes and text that allow us to annotate and that sort of thing. So yeah, lots and lots of features for how we actually lay out our board and make it look along here. A step further to the right again, and you'll see there's all of these layers that have been given to us as a default. So it's defaulted to a 2-layer copper board, so one layer of copper, then some insulation, then another layer of copper on the bottom. And that's what these first two are. So that's that F.cu is our front or top copper layer, and the BCU is our back or bottom copper layer. So those two important. I guess the main one, we're just going to do a single side for this particular design, so we're just going to route everything on the back layer. But for more complex designs you might use both top and bottom. You might even go in future subjects to a board that has more than 2 layers, and then you'd have some in between as well. But yeah, we're just going to concentrate on the back one for now. So then after our copper layers, we've got a fair few layers that are mainly relevant if we're getting our PCBs manufactured. The two that are quite useful if we get them manufactured by someone like JLC are the silkscreen ones. So silkscreen's like a plastic overlay that goes on top of the copper and allows you to do things like printing annotations and stuff like that. So you can label the different components on your board with just some text. That all gets printed and it's like this usually nice green with some text on it, and you can then more easily assemble your board because you can see where stuff's supposed to go and that sort of thing. But when we're milling in-house, like we will be for the first board that we design, we won't have silkscreen, it's just going to be copper, will be the last thing you see, so we won't use silkscreen for this particular demo. Then we've got a few other layers. Most of these, again, none of these are really going to be needed. The only other one we need to look at is edge cuts. So edge cuts sets the size of the board that we're going to design. For this video, I'm going to do that last, but in your first prac, for example, I'm going to give you some dimensions that are the maximum dimensions for your board. So you might like to set your edge cuts first so that you're able to design everything to fit within those dimensions that I give you. So, navigating through now a few of our other things that we've got going on. I'm going to go up to the top left here where there's this button for board setup. So board setup has a few things of importance. Firstly, it allows us to sort of set which of these layers we need. So I could actually go through and unselect all of the ones that I don't need. I'm not going to bother though because I can just also only use the ones that I do need. You can also change the physical stack up. So as I mentioned before, we will normally be working with single layer or 2-layer boards. Single layer is copper on just the top, for instance. 2-layer would be top and bottom. But you can also, when you manufacture boards through an actual PCB manufacturer, get ones that have lots and lots of layers in between as well. So that's when you could go to 4 layers all the way up to 32 layers in KiCad. And you might have sort of tracks that run in the middle that kind of can't be seen on the outside or whatever. But that's only necessary for those complex boards. For what we're doing in this subject, single layer is all we really need. If you want to get fancy, you might go to 2 layers just to make some of your routing a little bit easier for your assignment. And the other thing that I wanted to show you in this panel is that you can actually set up some constraints, some rules for yourself for designing your PCB. And the reason that this is helpful is because different manufacturing processes have different tolerances on their machines. So when we're getting them made at an actual manufacturer, like we will be for the assignment, usually their tolerances are quite fine. Like we can get quite small parts and everything else, and that'll all come out beautifully. When we're working with an in-house mill, it can be a little bit more varied depending on the exact mill that we're using. So it's a good idea to increase our tolerances a little bit, just to make sure that we're going to not end up with stuff that's sort of shorted out or stuff like that, just because of the size of our drill bits type thing. So I'm going to set some rules for us. I'm going to say that we want a minimum clearance between components of 0.5 mil. So that's going to limit how close together I can put 2 electrical pads. I'm also going to set a minimum track width of 0.5. So that's going to mean that when I route together different components, their width should be at least 0.5 mil. Again, we could probably get away with less than this with our in-house mills. Our in-house mills are pretty good. I'm just being conservative because then we definitely won't have any problems. Then some of the other ones that are useful, the annular width allows us to set how much pad there will be to solder onto. So given that this might be the first time that you've soldered, it might be helpful to increase that a little bit as well, just to give yourself a little bit more width to do your soldering on. So we could say that we want a minimum annular width of something like, maybe let's go with 0.4 and we'll see how that looks. We could always change that down later if need be. And similarly, we've got things like the minimum diameter of the overall hole. Down here, we've got the minimum through hole size, so how small the hole's allowed to be that actually goes through the board. I'm going to set that one a little bit higher than it is at the moment to about 0.8, just because that's going to make sure that we definitely can get the legs of components, standard components, through easily. So yeah, you can see there's a few other ones you can play with. Those are the ones that I think are probably important for us. So I'm going to hit OK on that. And that sets up some constraints that we'll then be able to work through the rest of the time. All right, so now we're up to the part where we actually want to lay out this board. So what we're trying to achieve is we're trying to make everything as compact as possible. So we want to make the board as small as we can so that we don't have to have as many tracks. And this is the same logic as when we build a breadboard, right? Like since first year, I've been saying, make sure you don't use more wires than you need to and everything else, because all of that introduces small amounts of extra electrical resistance and generally affects the signal integrity. It's not super obvious when you look at it for a simple circuit, but as you get into more advanced subjects where you'll be using higher frequencies and stuff like that, it will become very evident. So we want to try and keep everything close together. The other thing that we said we're going to do is we're going to add in a ground plane, and I'm going to talk a little bit more about that later, but for now essentially what it means is that any pin that's labelled with ground, we're just not going to connect a wire to. We're going to connect it to the ground plane later on. So at the moment we only care about routing together these other nets. And as you can see, it has little blue lines that tell us which components need to be connected where, which is going to help us to lay out things that need to be connected close together. So let's get started. Firstly, I'm just going to move this label out of the way, and then I might just space out these diodes so that we can get a clearer picture of which one's connected to which. So all I'm doing here is hovering over the component and clicking M, and that allows me to move it. Sometimes it decides to select a label instead of the component, so you just need to hit escape to get away from that. So yeah, that's just spacing them out. You can still see those connections where the different components will need to be routed together, so you can see that it's done absolutely nothing intelligent to try and lay this out. So let's firstly pick up diode 1, and I'm just going to rotate it around to place it pretty close to our track here. I might just put it so I can do that track fairly straight. Actually I might just lift it up so that we don't have to have a bigger board than we need. And I'm just gonna delete that label actually, because we don't really need that label. Then next up we've got, possibly might go for the diode 2. Yep. And just hit rotate again to try and line that one up, get it in nice and close. And again, we can delete some of these labels because none of them are actually going to be used for anything anyway. Then we have probably diode 3 next, I guess. Just go in ascending order. And yeah, it's telling us we can connect the ground there, but we don't really need to. So I might actually put it this way so that I can connect those nets together. I'll move diode 4 and see if that was a good decision. Yeah, that's a good decision, because then I can just put those together quite easily as well. Oh, actually those tracks are going to overlap, so I'll rotate this around actually. And we'll see how that looks. Again, just getting rid of some labels. I'm just pressing delete on my keyboard as I hover over. It doesn't like those because they're too close together, but there we go. And then the last one is our resistor. So I'm just going to pick that one up. And again, it doesn't really matter where we put the ground pin because we're going to connect it to a ground plane. So I'm just going to rotate it so that I can put it in nice and close to that pin down the bottom. Try to make it, it's not going to go horizontal for me. Cool, I'll just center it. Cool. So then what I'm going to do is zoom in a little bit so we can see it a bit clearer. And I'm going to start connecting anything that's one of these nets. Again, just ignoring the ground because we're going to connect that to a ground plane later. So I'm going to grab the route tool, which you can also just press X on your keyboard for. And you just want to click on the start of one node and go to another node that it's connected to. And you can see that it draws a nice straight line. Oh, actually I'm on the wrong layer. I want to put it on the copper layer. So just click the back copper layer before you start. So one node, then the next node, and it creates that route for us. And that looks a little bit small. I'm just going to check that it's actually made that 0.5 mil. Okay, it has. Just looks small to me. So that's fine. And then we just keep repeating that process. So now I'm going to go from this one over to that one. And you can see the little blue guidelines will disappear as we connect stuff the way that it needs to be connected. In this case, you can also go under the components. So this track is going to be flat. It's going to not, it's not going to be standing up or anything. So it's not going to stop us from putting a diode over the top of it. As long as we don't cross any pads, it doesn't matter. So I can put that one there and that's fine. Connect those two there. And this one needs to go over to here. It's a bit of a gross bend, but we'll allow it. And then this one just needs to connect up to there. And that is everything that is not a ground. Everything else looks to be connected fine. So now let's go through and add that ground plane so that we can actually connect those grounds together. And the way that we do that is we grab the tool to draw a filled zone and we just kind of outline the whole area. Right, I have to click and drop. I always mess this up. It's a click to start it. You pick the net that you want to go on. So we want to be on the ground net. We want to connect anything with a ground label. And then we go through and we draw our shape. And you don't need to leave a whole lot of clearance here. I might actually even bring this in a notch. I guess we could add slightly more clearance. Yeah, I'll add slightly more clearance just because it'll make it slightly easier to solder. It should still be pretty small. So there we go, we've got a little bit of clearance around each side. Probably can bring that one back in. So that's going to be our filled zone. And so then all of our ground will be connected to that. And then the next thing we need to do to finish this off is we need to actually fill that filled zone that we've chosen. So you can just right click on that draw filled zone button and click fill all zones, or you can press key on your keyboard. And that's going to paint in the entire board with that copper. So if you have a look now at our grounds, you can see that the grounds are sort of like a semi-hole. So they've been kind of carved out so that you can still put your pin in and everything and solder to it, but they've actually got electrical connections that take it out to that ground plane. And that ground plane is then also connected to this ground, and it just means that all of those grounds are connected together. Why do we do this? Well, for a small circuit, for a simple circuit that's low frequency like this, it's mostly just because it is easier. So it's convenient to pick a ground reference where we've got lots of things connected, because then we don't have to connect this one to this one and add a whole bunch of extra tracks. So it's convenient in terms of layout. It does improve the electrical characteristics of the board, because instead of having a lot of tiny little tracks with tiny little resistances, you've just got this nice big flat copper plane. The other advantage for the subject is it just makes it a little bit easier for measurement, because then you have a whole plane on which to put one probe while you probe around with the other probe to measure different things. So that's nice as well. Yeah, those are the main advantages in terms of a small board. As you get into in terms of a simple board, as you get into bigger and more complex boards, higher frequencies, that sort of thing, then it also helps with, well, it's necessary for the signal integrity of things like when you're working with USB or high frequency signals. So yeah, it's just sort of good practice at this point to use this to be able to make your own design easier, but also get those skills in place for when you're building those more advanced boards in future subjects. The other thing is that for more advanced circuits, you might also have multiple planes. So for example, you might not just have a ground plane, you might also have a power plane, or you might have separate ground planes for your signal ground and your power ground. Again, all of those concepts relate to more advanced circuits that you'll cover in future subjects, but it's just a skill set that's worth practicing and having. So I really recommend that you do your grounding with a ground plane and think about where that ground plane is to make your life easier. Cool, so that's our ground plane in. If we have a quick look at the 3D view for now, we can see we've got this nice little layout, everything's all in a row, it's nice and compact. And on the underside, we can see that we've got all of the light green is copper, and all of the dark green is where it's been carved out. So that's looking pretty nice. All right, so our little board's looking pretty good based on our layout and our 3D view. So now a good thing to do at this stage is just to do our design rules checker now that we think we've got everything the way that we want it. So click on that, run our DRC, and it comes up with at least two problems. And those two problems are to do with the annular width of our pins on the connector. So remember how we set up that minimum constraint to give ourselves a little bit more pad to solder onto? It's just saying we're a little bit below that minimum that we've set for ourselves. So what I'm going to do is I'm going to close this and I'm just going to select these pins, and I can actually just change the X and Y dimensions here. So we were only 0.5 mil off, so I might just add, actually I'll go up to 1.8, that way we're giving ourselves a little bit more clearance on both the X and Y dimension, given we've got a round hole and a square outline. And then I'm just going to repeat the same thing for our round pad. So for our round pad, I'm just going to go up to 1.8. So now if I rerun our design rules checker, hopefully that's enough clearance for it to be happy with life. It does now give a warning that we've modified the footprint, but that's okay. We can ignore that particular warning. I'm actually kind of surprised that the resistor was large enough. I'm just going to check that anyway. I mean, I guess I should probably believe it. Yeah, okay, it does have a fair bit of clearance. You could still make that pad a little bit bigger if you wanted to make your soldering job a little bit easier. So you could bump that up to, for example, 1.8 and 1.8. You can actually select multiple and change them both at the same time if they're the same type. So if it's a round one, you can change them all together. If they're square, you can change them all together. All right, so let's do that. That looks pretty good. I'm pretty happy with that. Back to the design rules checker, because there is still one more error we need to address, and that's the fact that we haven't yet defined the edges of our board. So even though we drew this nice filled zone, that's all just copper. It still doesn't know where the physical edge of our board will be. So this is where we go to that third layer I mentioned, which is our edge cuts layer. So we want to go over to edge cuts, just select it here, and all we need to do is grab a rectangle from the draw rectangle tool and go around. I always do this, I always accidentally select instead of click. So we want to click in the corner, we want to then move over to the other corner and click again. And that's going to be our rectangle for our edge cut. And that's it. So we can also inspect those dimensions, so you can see that its width is 25mm and its height is 15mm. So that's a nice, tiny, compact board. We probably couldn't do too much better than that. We could move the components slightly closer together, but hey, that'd probably make our solder job a little bit harder. So then one last check of our 3D design. Again, nice and compact. All of our traces are present and accounted for. And now when I run my design rules checker, it shouldn't have any complaints to give me whatsoever, other than those warnings about the fact that I tweaked our footprints. So that's all good. So now we've got our board all electrically ready to go. At this point we can export it export all the files we need to send to the mill. One other thing that is potentially going to be useful later on is to actually add your name to it, because for the first prac in particular, that'll allow you to figure out which board is yours. So you can do that with just text. You can draw text that gets cut into the copper on either side. I might even, if we have single layer board, you'll have to put it on the back as well. But I know that we've got some double layer board at the moment too, so I'm just going to put it on the top layer, and I'm just going to put my initials and drop it onto the board. So what that means is that then when I have a look at my 3D view, we'll have that updated little engrave where it'll cut out my initials. So then I'd be able to easily identify that this is my cute little board. So yeah, that's an extra step that'll be useful for pracs and stuff later on. Alrighty, so now we're up to the point where we can go through and actually get this thing exported and ready to be sent away for manufacture. So what we want to do that is we want to go into the File tab, and there's this Fabrication Outputs option. And the first option is Gerber or Gerber. I don't actually know how it's pronounced, but I go with Gerber. So we want to click on that one, and we want to select the layers that we want to include. And probably when you first open yours, they'll be more selected, like the silk screen and stuff. We might want those if we're going to mill it externally, like if we're going to send it away to JLC or an external fabricator. But for our in-house mill, we don't have anything fancy. We've just got our copper and our edge. So tick on any copper layers that you've used, tick on your edge cuts to cut around the outside. Make sure nothing's selected in this plot all layers one, so that should all be blank. And then you want to find somewhere to save it to. So I've already got an output directory here, but if you don't, just click there and search for the folder you want to use, select that, and then you want to click plot so that it generates everything. And then you also want to click this second button of generate drill files. So generate that as well. Once you've done both of those, which shouldn't take very long at all, head back over into your files to check that it worked. So that's the folder I saved them in here. And we can see that we've got the Gerber files for each of the layers that I cared about, as well as the drill files. So that's what our lab techs need to be able to actually physically mill your board. The exact process, like the things you include and stuff, is going to vary slightly if we're using an external fabricator like JLC or someone else. So I'll make a separate video on that. We'll cross that bridge when we come to it. For now, just go through that process to get your board sorted for the first practical or for any other in-house milling that we're doing. And when it comes back from the mill, you'll end up with something that's kind of shiny and coppery like this. So this is actually for a more complicated board that's the full power supply one. But hopefully you can see, I might actually stop sharing my screen so that I become bigger. So hopefully you can see there, it's nice and shiny copper on both sides. On one side we've got where we will put the components through. On the other side we have the actual tracks and pads that we'll solder to. So yeah, they're just isolated by carving out the copper there, and then the rest of the copper would be our ground plane. And it doesn't seem like my camera quality is super good, but there are little grounds there that are kind of cutouts to create that ground plane connection. So that's it for this video. That's the process that you'll follow for designing your first PCB. And that same process will be what you're walking through when you do the first prac. So a good idea to save all of the files from this demo so that you can easily come back to them and continue to build on them when it comes to doing that practical. Hopefully you found this useful, and I will see you in future skills videos.